All right. Next example. The question says, find the total heat flow rate through a composite wall shown below. This is the diagram. This is the composite wall. Solution. First thing first, what we are going to do is to record the necessary formulas, and we should do the solutions. Okay, from here, this is a 3D view of this composite wall. You know, join the 2D now, or relating it to what we've done earlier. We have we have the diagram to be this. This is wall A, this is the second layer, this is A, this is B, this is C, and this is D, right? This diagram is still this. And what you are saying is that the temperature at this region is 400 degrees Celsius. The temperature at this region is what? 60 degrees Celsius, right? Now, first thing first, we have to calculate what heat transfer. What was the formula that we obtained? We said that for a composite wall, the formula Q is equals to what? Change in temperature divided by the summation of what? Thermal resistance, right? Now, this is the formula we are going to use here. But before using this formula, let's draw the thermal circuit of this diagram. Let's draw the thermal circuit of this diagram. Let's draw the thermal circuit of this diagram. We are familiar with this. We can do the thermal circuit, right? Then we have this. For thermal circuit, we have this and this. B and C, are they in series or in parallel? They are in parallel, right? Series connection to what? Parallel. D, is D in series or in parallel? Series. The initial temperature is what? 400 degrees Celsius. Then the final temperature is 60 degrees Celsius. This is RTH of what? Of wall A, right? This is RTH of wall A. This one is what? RTH, the thermal resistance of what? B. And this is the thermal resistance of what? Wall C. This is the thermal resistance of what? Wall D. Then we said we are using this formula. Change in T, Q is equal to change in T divided by summation of RTH. Now, our change in T is what? T1 minus T open bracket N plus 1, right? From the formula we obtained earlier. But in this case, we are giving the initial temperature to be 400 and we are giving the final temperature to be 600. Hence, change in T in this case is 400 degrees Celsius minus 60 degrees Celsius. We've gotten this. But now, how do we solve for summation of thermal resistance? From the thermal circuit, we said that RTA is in parallel to RTB, also to RTC, then in series to what? RTHD. Meaning we are applying the knowledge in electricity to this. And what we know is that resistor in series is the summation of individual what? Resistor. The equivalent resistor, when we have resistor in series, the equivalent resistor or the equivalent resistance is the summation of individual resistor. Meaning, from here, to get the total resistance, to get summation of RTH, it means that RTHA, thermal resistance of wall A, right, plus this and this are in parallel, so you have to solve in parallel. RTHB parallel to what? RTHC plus RTHD. Then you get the value of this, get the value of this, get the value of this. Then add it up. You are done. But now, how do we get the value of RTHA, RTHB, RTHC, RCHD before using this formula. Recall that thermal resistance has its formula to be what? To be X divided by Ka. Right? This is what we know for thermal resistance. This is what we know for what? Thermal resistance. Okay, let's solve the thermal resistance for each walls. For the wall, what does the question ask us to calculate again? Total heat flow rate. For this wall, for this composite wall, we are giving this place to be 10 centimeter. We are giving the distance, the thickness of wall A to be 3 centimeter. We are giving the thickness of these layers, wall BC, to be 8 centimeter. We are also giving the thickness of wall D to be 5 centimeter. And we are giving B here to be 3 centimeter and here to be 7 centimeter. Now, we want to use this formula, right? Applying this formula to the first wall, which is wall A, it means the thermal resistance at wall A is equal to what? The thickness of wall A divided by the thermal conductivity of wall A times the what? Area. So these are the thermal conductivity of each walls. Are we together? Are we together? Any question? Now, we want to get the value of thermal resistance of wall A. What is the thickness of wall A? The thickness of wall A is given to be what? 3 centimeter. The thermal conductivity of wall A is given to be what? 150 watts per meter degree Celsius. The area of wall A is unknown. How do we solve the area? Yeah, we are giving the thermal conductivity of wall A to be 150, right? How do you solve the area of wall A? From here, imagining you are bringing out wall A from this diagram. Let's bring it out one by one. Now we are dealing with wall A, Abi. From this is the given question. Say we are bringing wall A out from this diagram. It means we have something of this. Abi, this is wall A. We are bringing wall A out of this composite diagram. This is wall A. From this diagram, considering wall A, from here to here is what? 10 centimeter. Considering wall A, from here to here is what? Is what? Wall A, 10 centimeter. The summation of 3 and 7 will give us what? 10 centimeter. This is wall A, 10 centimeter. So area of wall A, but in this case now, observe, your thermal conductivity is in meter and not centimeter. It means you have to convert from centimeter to what? Meter. That will be what? Convert 10 centimeter to meter, we have 0.1 meter. Area is equal to 0.1 times 0.1. And this is equals to what? 0.01 meter square. Right? Now, RTH, the thermal conductivity of wall A is equals to what? Converting 3 centimeter to meter, we have 0.03 meter. So we have 0.03 divided by thermal conductivity of wall A is given to be what? 150, right? Times the area is what? 0.01. What's the value? We've gotten 0.02 for the thermal resistance of wall A. Now, for wall B, we are still using this same formula. Okay, considering this composite wall, let's bring out wall B. We have the wall to be something of this. This is wall B, right? For this composite wall, from here to here is what? For wall B, from here to here is what? 3 centimeter. 3 centimeter. For wall B, from here to here is what? You know, you are doing it in this manner, like this. Okay, from here to here, wall B is what? 8 centimeter. Then from here to here is what? 10 centimeter. 10 centimeter. Okay, now from here, x of B is what? 8 centimeter. Abi? Which is 0.08 meter. We are converting to meter now. The thermal conductivity of wall B is given to be what? What's the value for thermal conductivity of wall B? 30 watts per meter degree Celsius. The area of wall B will be equals to what? 3 times 10, Abi? But in this case, we are converting to what? Meter. Hence, we have 0.03 times 0.1. Converting 3 centimeter to meter will give us 0.03. Converting 10 centimeter to meter will give us 0.1 meter. Converting 8 centimeter to meter will give us 0.08 meter. So that's what we are saying. The area is equals to 0.1 times 0.03. Then this is the thickness. Now let's get the value of the area. Area is equals to what? 0.003. Right? Alright, we've gotten the area of wall B. We know the thermal conductivity of wall B. We also know the thickness of wall B. Using this formula, we have RTH of B, the thermal resistance, to be what? What's the value of the thickness of wall B? 0.08 divided by the thermal conductivity is what? 30 times the area is what? What's the value? 0.89. Right? Moving on to the next one, wall C. For wall C, let's bring out the wall. In this composite wall, let's bring out wall C. Bringing out wall C from this composite wall, we have something of this nature. This is wall C, right? From this composite wall, from here to here is what? 8 centimeter. From this composite wall of wall C, considering wall C, from here to here is what? 7 centimeter. Then from here to here is what? Is what? Observe. 10 will be constant. 10 will be constant all through for each wall. 10 is constant. This one is what? 10, right? 10 centimeter. Any question? No question, right? Now, from here, the thickness of wall C in in meter will be what? 0.08 meter. Converting 8 centimeter to meter. The thermal conductivity is given to be what? What's the value? 65 watts per meter degree Celsius. The area will be equals to 0.1 times 0.07. Right? Converting 10 centimeter to meter, we have 0.1. Converting 7 centimeter to meter, we have 0.07. Let's get the value. 0.007 meter. Hence, the thermal resistance, okay, meter square. The thermal resistance of wall C is equals to what? Using this formula, 0.08 divided by 0.007 times 65. What's the value? 0.18, no approximation, right? Okay, moving on to the next word, which is word D. Word D. For word D, from this composite word, bringing out word D here, we have something of this. Right? This is word D. From here, considering word D, from here to here is what? 10, right? How do we get 10? 7 plus 3 will give us 10 centimeter. For word D, from here to here is what? 5 centimeter. From word D, from here to here is what? 10 centimeter. This 10 centimeter, right? Now, we can now write that x of word D is given to be what? A meter, 0.05 meter. The K of word D is given to be what? 50 watts per meter degree Celsius. Now, we can get the area by multiplying this and this. 0.1 times 0.1. Then we have 0.01 meter square, right? Any question on that? Okay, from here, let's get the value of the thermal resistance of word D. We then have that RTH of D is given to be what? 0.05 divided by 0.01 times 50. What's the value of this? 0.1. Now, initially or earlier, we said that to get this is the formula we want to use. This is the formula we want to use for the heat transfer. We already know change the temperature to be 400 minus 60 degree, right? Now, to get the summation of RTH, we've calculated RTH of word A, we've calculated RTH of word B, we've calculated RTH of word C, and we've calculated RTH of word D. And we said from the thermal circuit, we said that word B and word C, they are in parallel. This is what we are saying. This is thermal resistance of A, right? This is RTHA. What was the value we got? 0.02. RTHB, what's the value? 0.87. RTHC, what was the value? 0.18. For RTHD, what was the value? 0.1. Now, to get the total thermal resistance, it means that this and this are in parallel. That's why we are having this formula. Now, let's solve for parallel resistance. And we know for parallel, 1 over R total is equals to what? 1 over R1 plus 1 over R2. So we are applying that knowledge here. It means that 1 over R total in this case, let's call the total resistance in this case to be RTHQ. Any question on that? Equals to 1 over RTHB plus 1 over RTHC, right? From here, it means that RTHQ is equals to RTHB times RTHC divided by RTHB plus RTHC. Any question on that? Now let's substitute the value. RTHQ is equals to RTHB is what? 0.87 times 0.18 divided by 0.87 plus 0.18, and this is equals to what? 0.149, meaning that you can withdraw your thermal circuit as what?
0.1.
Abi, now this is still RA, which is what? 0.02. Now the parallel combination of this guy, you solve it to be what? 0.149. You have 0.149. What do you have here? 0.1. This is RTHA. This is RTH. We said we denoted it as what? RTHQ, Abi. Then this is still what? RTHD. Hence, the summation of the thermal resistance, is equals to what? RTHA plus RTHQ plus RTHD. Subtracting the respective value, we have 0.02 plus 0.149 plus 0.1. What's the value? 0.269. So therefore, to calculate the total heat transfer using this formula, we have T1 is what? 400 we have 400 minus 60 divided by 0.269. This is equals to what? 340 divided by 0.269. What's the value? We have that if 1263, what will be the unit? Watts per meter degree Celsius. Then we are done. Oh, sorry. Yeah, just what? We have 1263.94 watts. Then we are done. So this comes to the end of this video. In the next video, we will be talking about conduction of hollow cylinder, how it works, and examples. All right, see you in the next video. Don't forget to like, subscribe, comment, share.